and I'm an analyst in the Ecosystems Analysis team at the Joint Nature Conservation Committee. We've been developing our capabilities of using Earth observation to assess habitat condition, and as part of this have focused on how EO can help monitor the condition of peatlands and provide evidence for the effectiveness of restoration measures. UK peatlands cover around 3 million hectares, roughly 12% of the total UK land area. They play vital roles in providing habitat for rare and threatened species, contribute to water regulation and filtration, and to carbon sequestration. Over 80% of the UK peatlands are in a degraded state due to anthropogenic activities such as land conversion, drainage, extraction, and burning. In this drained state, peatlands become carbon emitters, releasing large amounts of stored carbon back into the atmosphere. Peatland restoration has been recognised as a nature-based solution which can help us to tackle biodiversity decline and climate change. Huge investment in restoration efforts has been made from both the UK government and from the devolved governments, with restoration featuring heavily in a number of key policy areas. So this highlights an important area where evidence is needed in order to assess current condition of UK peatlands, to spatially prioritise areas where interventions are needed, and to monitor how effective interventions have been at restoring these habitats to a good condition. So far, current methods for assessing condition has relied on experts in the field, conducting ground-based assessments. So this often involves surveying for indicators of condition, such as looking at areas of bare unvegetated peat, the amount of sphagnum moss cover, and the wetness of peat soils. So this can be time-consuming, expensive, and often restricted, so particularly up in remote upland areas. So this is where EO can provide a cost-effective means for aiding assessments. Previous work in the area has focused on mapping the extent of bare peat as it is a visible indicator of peatlands in poor condition, often as a result from erosion, drying, and damage from overgrazing or trampling. So this has involved classifying these features on a fairly coarse scale to create national scale maps. The challenge, however, is bare peat can often occur in small patches as well as those large expanses, which can be hard to pick out from satellite data at lower resolutions. So also on this national scale, it may be less useful for land managements actually working on the ground. So a previous study by UKCEH and the James Hutton Institute looked at first classifying bare peat areas using very high resolution imagery, such as aerial photography, and then using that information to scale up to scale to Sentinel-2 imagery, giving an estimate of the amount of bare peat within a 10-meter pixel. So that is a way of capturing some of that detail of these smaller patches. So we're focused on developing this method further, first through a pilot study and now through a project under Copernicus User Uptake, funded by the Caroline Herschel Framework Partnership Agreement. This is working with partners from Natural England, Welsh Government and Forest Research to assess bare peat across multiple sites in the UK, both with VHR data and with a time series of Sentinel-2 imagery to see whether we can detect changing condition over time. So at the local level, for each site, we collated very high resolution images from aerial photography GB service, which is at 25 centimeters spatial resolution. And we took all the available dates from 2015 to 2020. So using combinations of the spectral bands, we were able to calculate various vegetation indices and use these to develop threshold rules to separate out the bare peat from the rest of the image. For instance, here we've used normalized difference vegetation index, an index commonly used for representing primary productivity. So using this method, we could quickly highlight in the images these areas of bare peat at the fine resolution. This method was combined into a thresholding app, which we have developed using R Shiny to provide an efficient way of dynamically adjusting thresholds and iterating through lots of images. So what about at the larger scale? This one is one of the sites from Brecon Beacons, which is roughly 305 kilometers squared. So this would be very time consuming to identify the bare peat in the VHR for the whole site. However, by doing this process with just a few representative regions, including some of the more degraded sites, we're able to extrapolate the predictions out across a wider landscape using regression modeling. So this uses random forest algorithms to train a model based on the information from the high resolution imagery, as well as other important predictors of climate and slope to predict the amount of bare peat cover per 10-meter pixel in the Sentinel-2 imagery. So we could then apply these models across a time series to extrapolate our predictions temporally and see how the predicted cover changed during the time period. This comparison shows how the model picked up those changes evident in the imagery above. So we found that these maps were able to predict changes in bare peat cover between years, even with models trained on relatively small amounts of data. So these were able to highlight changes in erosion, where the extent of bare peat had expanded between the years, as well as where vegetation had recovered. So one of the sites we looked up in Scotland, it was a peatland site which had been forested and undergone felling. So by comparing areas here where known restoration measures had been carried out, we could compare how effective different management measures had been. And looking into this further, the comparisons maybe with other sites, we could help to inform schemes and which methods would be best to use for restoration. Overall, we've learned a lot about the method through this work and its limitations. Working alongside our partners and their site teams throughout the project has been invaluable in understanding what is being picked up and how accurate our model predictions are. Through this process, we're narrowing down the conditions to best model bare peat, for instance, using only summer imagery to train, as well as make predictions, as well as using multiple years of VHR imagery in order to improve model accuracy. We also can't take our predictions at face value. For instance, in this image here, you can see there's a comparison between years where change has been flagged. So, however, this is actually due to water management at one of the sites, with one of the fields flooded during our imagery compared to in another year. So, as opposed to this being an indicator of a declining condition. And this was also highlighted in our validation with the stakeholders, where site experts were asked to digitize areas where they would expect bare peat to be, particularly due to management or climate influences, as well as known vegetated areas. At the Humberhead site, this produced quite an accurate result, with over 70% of their polygons deemed accurate, with inaccuracies due to the water management issues. So at the Dark Peak site, there seemed to be good spatial correlation with the identified bare peat areas, although more uncertainty around areas predicted to have lower cover values and inaccuracies noted where there's areas of heather cutting. So overall, the feedback from our partners and other stakeholders has shown that the work is promising and this has an operational use in helping to inform where restoration measures should be targeted. So this work has shown us a number of challenges. So we're still gathering feedback as to how good a method it is and at what scale users would find most use to them. We've shown here that we can produce maps at both local site level as well as scaled up to the regional level. So being able to make predictions at different scales can allow us to adapt to problems and make use of the most appropriate data. So to that effect, we could explore using other data sources to inform the analysis, such as drone imagery or other VHR sources, and investigate how radar might be able to help distinguish these features. Uncertainty from the initial image detection with the VHR is also carried over into the scaled up model versions. So one challenge is improving this detection to be as accurate as we can. For instance, so we could use more sophisticated image detection methods or explore the use of texture indices as well. And as well as bare peat, what other features would we be able to pick out for monitoring restoration? So potentially identifying other indicators such as wetness or particular vegetation species. So overall, it's a really exciting area where, alongside key partners in the field, we've been able to develop ways of monitoring peatland condition and changes in condition over time. Analyses such as these can help provide an indication of how successful restoration measures have been and develop and demonstrate how investing in nature-based solutions such as this can help mitigate climate change and meet the societal challenges we face today. So thanks, just want to acknowledge everyone who's been involved in the project with us and happy to take any questions. Thank you very much.
So hello and welcome to this talk about rapid satellite assessment methodology development as part of the Welsh Peatland SMS project. So my name is Alan Radbourne and I get the privilege to present work that can only accredit really to my colleagues at UKCEH and the wider Welsh Peatland SMS project. So the purpose of this presentation is to outline a little of what we've been developing to move along a rapid ground truth protocol to train a dataset for broad-scale peatland condition assessments via freely available satellite imagery. So to begin, we developed a simplified field protocol to allow rapid data collection in the real world that would train the imagery model for classification of functional condition assessments. The protocol was aimed so anyone would be able to collect basic site and vegetation analysis on a peatland site. So the protocol is freely available for anyone to use. It has been integrated within the Welsh Peatland SMS project, and we hope it will be utilised by many other peatland assessments to continue to build a large peatland database in Wales and beyond. So the protocol is simplified, so it wouldn't give you a thorough peatland condition assessment. Some information of general condition can be inferred from the protocol, but primarily the data collected was aimed at what can be seen from a satellite to classify images. So this top-down image obviously is a very different view than what we get when we are out in the field. So initially some of the things may seem strange to collect that sort of information, yet ultimately it makes sense when applied to a model, to the training data on a broad scale. So as mentioned, this protocol has been integrated into the Welsh SMS programme, and data collection has taken place across Wales, primarily conducted by the Snowdonia National Park Authority, so the lead partner of the Welsh SMS project. And to aid the speedy and simple data collection, Rachel Harvey, one of our colleagues at SMPA, has developed a QField app data collection protocol to run alongside these rapid assessments. So this allows for a simpler, paper-free data recording and digestion into an Excel spreadsheet. And it has proven to be a great way to collect lots of data in the field and upload it onto a spreadsheet, as long as you've got a decent phone battery. So the protocol that is applicable across all data collections as well, so you can adjust that, and it is also freely available through the Welsh SMS programme. And so the data, well, there has been 1,300 locations surveyed across Wales, with the main location being upland blanket bogs, because we love those here in Wales. This data has then been used to train an initial classification of 30 peatland classes based on peat depth, vegetation cover and artificial drainage. So the satellites used are freely available data of Sentinel-1 and Sentinel-2. And without wanting to go into too much detail, Sentinel-1, the picture on screen, which I must say that I cannot claim any credit for this picture, sorry, I did not take that one, is a synthetic aperture radar with a 5-meter resolution that does not pick up spectral differences, yet can acquire data independent of weather conditions, so whether it is cloudy or not, which of course in Wales is a big deal. Whereas Sentinel-2 is a multi-band spectral imager with a 10-meter resolution that can detect changes in surface colour, but it is only visible in daylight hours or on cloud-free days, which obviously is not something that happens too often in Wales. In fact, Jenny Williamson, so our UKCEH Earth Obs expert for the SMS project, thinks that this might have only happened on one day in recent history, or since Sentinel-2 has been released. And that was the 29th of July 2018, with this fully cloud-free day across Wales, which is very exciting, and bless Jenny, it took her ages to stitch this image together, so we wanted to give it as much airtime as possible. Because as you can see, Sentinel-2 data provides a lot of detail and the true colour imagery looks great, it looks right, and it is a good picture of Wales. However, this takes a lot of processing, with the images from different passes needing to be processed to remove the changes caused by sun angle, and it's obviously only available at large scale on cloud-free days. Now obviously if you're just focusing on a small site, then you are going to be lucky on some days without cloud cover, but for a large image like this, we reckon just one day in the last, 3 years or more. So due to past project understanding and issues mentioned above, Jenny has been using Sentinel-1 data to train the condition assessment. And this is an example of 1 month of data from Sentinel-1. So this is 12 images being downloaded in total, and the main limitation on doing this, she found, was actually computer memory space, as all the processing has to be done on Google Earth Engine. But once this is done, it has provided an opportunity to generate images of height, aspect and slope data for Wales that can be seen on screen. So this data has been reprocessed to the same resolution and projection as the ground data collected, ready for classification analysis, using the training data we have collected. So the Welsh SMS project still has a bit of time to go, so unfortunately I cannot show you the fully processed classifications or training data set and give you final outputs, because these are all still processing and things that will be coming out over the next 6 months or so. And obviously COVID isn't helping the situation, as it is not helping anyone's situation, as Jenny's poor laptop and internet is struggling to keep up with the massive image files that are having to be processed to take this forward. But the next steps will be to clip the Sentinel-1 layers, so height, aspect and slope data, into the Peatland map. Then develop the training data set to cover the currently underrepresented land cover types of croplands, intensive grasslands, lowland raised bogs and forested peat. And then it'll be time to give it a go and run a supervised classification of peatland land cover in Wales using the training data, 12 Sentinel-1 median monthly values and height, aspect and slope data. So we think the potential for this method is great for a rapid assessment. Although we say rapid, obviously the Earth Obs expertise and the time to process these images and run this still is quite large, but for a large scale compared to getting out there and collecting all the really detailed data and doing an assessment that way, this has a great potential for broad scale, or in this instance a national scale peatland condition assessment. That could, with continued rapid protocol methods development and data coming in, feeding more and more training data for Wales and beyond, this could develop further to confidently assess peatland condition on a broad scale and see changes over time as more and more years of Sentinel data become available. So thank you for joining us today. I hope you have found this an interesting aspect of the Welsh Peatland SMS project and UKCEH's work on peatland condition. Again, I cannot claim expertise in Earth observation or claim much of the work presented here today, so I just want to thank all of my colleagues for putting the time and effort into this presentation and for me to get all the glory being on screen. But please do get in touch and speak to Rachel at the exhibition session as part of this conference if you would like more information, or get in touch with us directly. So, diolch yn fawr yn gwrando. Thank you for listening, and hopefully we will hear from you soon if you've got any questions. Thanks.
Today I'm going to discuss some of the work we've been doing on Dartmoor over the last 4 years. For those who don't know, Dartmoor National Park lies in the southwest of England, between Exeter and Plymouth. It contains an extensive area of upland moor, much of which is covered by blanket bog. Uses of the peatland have been varied and include domestic and commercial peat cutting, tin and china clay extraction, granite quarrying, drainage for agricultural improvement, grazing with and without burning to improve pasture, forestry, military activity, and more recently recreation. This has led to much of the peatlands being in poor condition. The question was, how much and how bad? In 2016, we were commissioned by Dartmoor National Park Authority and South West Water to map the extent of and damage to peat within the moorland section of Dartmoor. We're lucky based here in the southwest, as the Terra Southwest project flew a high-resolution airborne geophysical and LiDAR survey over Dartmoor in autumn 2013, giving us a wealth of high-resolution remote sensing datasets to work with. One of these datasets was airborne gamma-ray spectrometric data. All bedrock materials, especially granite, emit radionuclides, here represented by the red arrows. Radiation emitted from the underlying bedrock is attenuated by overlying soils. The amount of attenuation is in part dependent on the thickness of the soil, porosity, saturation, and density. On the left, you can see the spatial distribution of radiometric dose across Dartmoor, with darker areas corresponding to areas with deeper peat. By collaborating with Ralph Fife, Lauren Parry, and Tim Harrod, we were able to amass 1,779 peat depth measurements with which to train and test a peat depth model without a single day in the field. Stepwise, multiple linear regression indicated that radiometric dose and slope derived from LiDAR data were the best model for peat depth. From this model, we mapped peat depth with an estimated uncertainty across the extent of the granite. We estimated an area of 158 kilometres squared of peat, at least 40 centimetres thick. Of this, 96 kilometres squared was overlain by bog vegetation, as you'd expect, but a further 61 kilometres squared were overlain by grass, which may have been missed if vegetation cover was being used to map the peat extent. Using published bulk density and carbon content values, we estimate 13.1 megatons of carbon are stored within the peaty soils of Dartmoor. Now we have an estimate for the extent of peat. The next thing was to understand the extent and the distribution of the damage. We mapped gullies and erosion features, drainage ditches, peat cuttings, and bare peat. Details of the methods for all these different types of features can be found in our landscape ecology paper. However, I'm going to outline the method used to map gullies and erosion features here as an example. So we took the 2-metre resolution LiDAR data. They were detrended by removing a smooth digital surface model to leave the high frequency variation. A threshold analysis was then run to identify depressions. And then we also calculated the ability of these depressions to accumulate flow, enabling those most likely to be erosive to be identified, here shown in red. Overall, 51,865 erosion and gully features were mapped. Assuming the water table drawdown occurs up to 3 metres from the edge of erosion features, a hydrologically affected area of 12.6 kilometres squared was estimated for erosion and gully features. In order to validate this, a selection of features was surveyed to assess the accuracy of the digitising work. The lengths of drains, gullies and erosion features and areas of peat cuttings and bare peat were measured in the field, and these were compared to the lengths and the areas digitised on screen. We can see that the peat drains were the most accurate and bare peat the least, but all features mapped with sufficient accuracy to be of use. If we look at the final data produced, we can see the total number of mapped features, the areas they cover, and how the damage is distributed across the moorland. This has facilitated strategic planning of restoration at a national park scale. I also think it's fair to say that given that 9.2% of the Dartmoor peatland area was identified as significantly and directly eco-hydrologically degraded, the situation was worse than expected. At a hillside scale, this mapping has allowed us to understand how the different types of damage fit together. Commonly, bare peat areas occur where it's flatter, transitioning to gullies as the topography steepens coming off the side of the hill. Finally, the right-hand column shows how the high-resolution mapping has sufficient detail to understand where the damage is at a site level and start planning appropriate restoration. As a supplementary task, we were asked to map the eco-hydrologically intact bog, an example of which is shown here. Being as far south as we are, textbook hummock and hollow peatland topography doesn't form. However, if we look through the carpet of Molinia, you can see sphagnum is the dominant vegetation. From experience and work on the ground, we knew that functionally intact bog is less bumpy than degraded bog with tussock grasses, heather shrubs, or bare peat areas. We used known extensive functionally intact peat to determine a bumpiness threshold in the detrended digital surface model. We then extracted all areas with vertical spatial variability below this threshold. These were then cross-checked using field validation and near-infrared aerial photography. A total of 3.6 kilometres squared was identified as eco-hydrologically intact, and this enabled restoration to be targeted to protect these remaining fragments. At a site level, the practical and economic effort of restoration can be estimated and optimised using data derived from geospatial datasets. Using LiDAR data, we were able to model and map the fewest numbers of blocks to rewet any given area. To simplify the method, first we mapped erosion features, then we mapped contours, placing a point where these intersect. This is repeated using different space contours for different size blocks. The larger the contour spacing, the larger the block. We are working to improve this method to cover a wider range of block types using feedback from the South West Peat Partnership, who are carrying out restoration on the ground. I will finish with a taster of our current project. We've been tasked by Dartmoor National Park to map habitat class and habitat change across the national park. This is a simplified workflow, but we've taken cloud-free, early spring, and midsummer Sentinel-2 satellite images. These have been combined with 3,838 photo-interpreted pixels, classified according to the level 4 of the UK Habitat Classification Scheme. And these have been input into a random forest classifier. This has produced a 10 metre squared resolution habitat class map of the whole of the Dartmoor National Park area. We're still working to produce the pixel accuracy map. We're getting an overall user's accuracy of 68%, meaning that if a pixel is mapped at a given habitat class, then the probability that this is correct is 68%. Some classes have higher accuracy and others lower. However, if we look at hundreds of square kilometres covered and consider how long this would take to do manually, then this work is a leap forward in understanding which habitats are where within the national park. If we zoom into a section of upland, we can see that the classifier is identifying blanket bog covered in acid grass and heath in pale green and purple, bare peat in black, flushes in the pale blue, water in the darker blue, and intact blanket bog in the pink. If we compare this to the CEH 2015 land cover map, a commonly used land cover map, most of the area would have been classed as bog. So the improvement in detail is quite striking. As I said, it's still a work in progress, but the tool is being designed so that habitat classification can be rerun every year and the change in vegetation at a 10 metre squared resolution be monitored. Following restoration, we may expect to see an immediate increase in water and a decrease in bare peat, and then hopefully over the longer term, an increase in intact blanket bog. A presentation on this project is available following the Sweep Expo at the address on screen. Finally, I'd just like to take a moment to plug our Miles on the Moors report, now available online, and to thank our numerous project partners shown here. Thank you.
Hello, my name is David Large. Thank you for inviting me to speak today. What I'd like to present to you is the application of InSAR techniques to peatland management, carbon accounting and loss prevention. If you're unfamiliar with InSAR, it's a satellite method that measures surface motion. And surface motion is a really powerful indicator of peat condition. And rather than focusing on the kind of background to InSAR today, what I really want to focus on is the practical applications of the InSAR method, because it enables really substantial areas of peat to be and their condition to be quantified. So a bit of theory then, just to give you a clue as to why it might work. Peatland has peats fall through the process. You have the ecological processes, the hydrological processes, and the mechanical processes. They're all interconnected and they're all equally valid. And the mechanical processes are represented through the surface motion. This has been known for some time. If you look at the top right-hand diagram there, you can see some data from Harvey and Hebda in 2018, where they illustrate peatland surface motion over an 8-year period for sites in two quite different conditions, a sphagnum sedge site and a sphagnum shrub site. And you'll see that those graphs really look very different. Their characteristics are substantially different. Now, surface motion is not easily studied in the field. It's not easily studied in the field because it's time-consuming and it's difficult. But using satellites, you can get coverage very quickly, very efficiently over very large areas at really quite high resolution, which is appropriate to peatland monitoring. And this is what the InSAR does. So just taking you through our process, we start off with ESA Sentinel-1 SAR data. That's collected every 6 days. It's not affected by cloud cover in any substantial way. We then put it through an advanced InSAR processing technique. And that's really important because traditional processing technique you may be more with do not give continuous coverage over vegetation, but there are a couple of more advanced processes that do, and we need to have that coverage if we're going to get the time series of surface motion and the characteristics of surface motion. From that, we then produce these time series that you can see in the top right-hand image there. And these time series, the top one there is a peat in good condition. It's 3 years worth of data. And you can see the very similar oscillations in the surface that were observable in the data of Harvey and Hebda. And over time, the surface is going up. The one at the bottom is subsiding. It lacks the clear seasonal cycles, and that's a degrading peat. And this time series data of the surface motion is really information rich. So we then take these time series after the InSAR processing and we extract and classify the surface motion characteristics. And in particular, we look at things like the trend, the amplitude of seasonal oscillations, the timing of seasonal oscillations, the regularity of those oscillations, their shape, and then the residual variance. And with those classifications, we compare it to what we observe on the ground. And we've done that over many, many hundreds of sites across Scotland now. So the validation is really quite robust, but I will not be presenting that data to you today. I'm going to focus on those examples, the applications of the method. So the first example I'd like to illustrate is the evaluation of forest to bog restoration techniques. So this is based on 600 blocks of forestry that were felled in the RSPB Forcenard site, north of Scotland, up in the Flow Country. And you've got two groups here. You've got one group, which is the blue circles, and one group, which is the orange circles. Our vertical axis is the mean velocity, which is the mean subsidence rate. And when it's in bad condition, it should be a low value in that axis. It's subsiding rapidly. And then as it recovers, the rate of subsidence declines. And on the horizontal axis, you have time since felling. And you can see that both the orange circles and the blue circles show very similar trends. The blue circles, they were treated as fell to waste before 2010, so basically getting rid of the forestry and leaving it. And then post-2010, the orange circles, those areas received intensive ground treatments. And what this shows is although they're following the same trends, the orange circles are reaching the same level of restoration about 7 to 8 years earlier than the previous treatments. So these more advanced treatment techniques are giving you a marked advantage. The next thing I'd like to focus on is this aspect of loss prevention, and in particular, the losses that you might get associated with a bog burst. We have a hypothesis that we formulated over Scotland, and that hypothesis was that very high amplitudes of surface motion would be associated with a risk of peat failure. Now, peat failure causes huge losses, and one of the best examples of that was what happened in Ireland this year. We had the thing called the Drunkirn peat failure, It occurred in County Leitrim on the 29th of June, and roughly 200,000 cubic metres of peat headed downhill. It devastated farm lands, it damaged water quality, it caused loss of reputation for those managing the land in the neighbouring forestry. So those losses are considerable. And we examined that site in great detail. And what we observe is shown in really these two central images. On the left-hand one, we have a map of vertical motion, and on the right-hand one, a map of lateral motion. And what we're showing here in the reds and the blues are extreme values of motion, not just the background motion, but the extreme values of motion. The outline of the peat slide area is shown in white. You've got a white line going around that, and that was provided by Owen Holohan of UCD. And what you can see is on the left-hand, this is from the 15th of March, so we're about 3 months ahead of the failure. We can see that the left-hand part of the failure area is going up rapidly. At that point, it's showing extreme upward motion, and at the same time, we're getting horizontal motion, lateral motion, shown in the right-hand image. So we've got extreme upward motion and lateral motion simultaneously. And that is associated with a very wet event. If we step forward, we go through a drought period, and then during that drought period leading up to just before the slide on the 25th of June, the area that was previously wet collapses. You see that in the left-hand image, we get extreme collapse. And then the right-hand image, we see that the extent of horizontal movement has expanded. So we're getting a really clear signal that the extremes in the surface motion are associated with a risk of failure in this particular example. And the plan is we'll develop that further and test this hypothesis more fully. But it's quite a good indicator at this stage that we can see anomalous behaviour in InSAR. So the final set of examples I'd like to focus on is the classification for condition monitoring and carbon accounting. And it's based on this table. So what we have in this table is in the first column, we have our InSAR class, and that goes from 1 to 4. And we have two class 4s, a 4A and a 4B. And they're both near natural conditions. The 4A is what you might think of as your ideal near natural sphagnum system. And the 4B is what you might think of as a near natural margin to, say, a mesotope. So you've got the slightly drier margins where you go from the sphagnum dominated, say, the neighbouring river systems. We then have the surface motion characteristics in the next three columns. You've got the velocity, which is the multi-annual velocity, the amplitude, which is the amplitude of the seasonal oscillations, and the timing of those oscillations. We then have a condition statement and a ground description that we can use to validate it in the field. And then finally, in the right-hand column, we have attributed emission factors to these conditions, and that's based on the data from Evans et al. 2017. And we have had to interpret that data to spread it out, because what we see are very much transitions from one state to another. We pick up continuous transitions. That is not really implicit in that data. So we've had to fill in some of the gaps for emission factors by our best available approximation. And we have given nice substantial ranges for those values. So putting that into practice, the first example is again a forest to bog restoration progress. We've used the 4 classes going from 1 to a 4A, 4A being the target class in this case, which was a sphagnum-rich end member. And we're looking at the progress over 3 years, from 2016 to 2019. And as we go through those 3 years, you can see you've got class 1 in red, class 2 in yellow, class 3 in green, and class 4 in dark green. You can see going from 16 to 17, and 17 to 18, 18 to 19, the proportion of class 1 diminishes. Class 2, which is early re-wetting, increases markedly. Class 3 increases more slowly, and class 4, our optimal class, very slowly indeed. And that corresponds, if we use our range of emission factors, to probably a net reduction in emissions of between 0.5 to 1.5 tonnes per hectare over that period using those particular emission factors. And then the final example I'd like to show you is the application to a really large area. So we've taken 1,400 square kilometres of the flow country. You can see it in the top right image there, in the top, far, far northeast Scotland. And we've classified that using only 3 classes. We haven't gone for the subtle differentiation within the re-wetting classes. And we've got class 1 and 2 class 4s. And what that gives you is for the whole area, we've got 57% of that's degraded with a mean emission of 6.7 to 3 tonnes, somewhere in that region, 6.7 to 3 tonnes of CO2 equivalent per hectare per year. And then we can zoom into higher resolution, then obviously higher resolution still, as you saw in the previous image. And for that slightly better area in the centre, we've got about 46% degraded using our scales, and obviously a better emission factor for the site as a whole. So what I hope this shows you is that the InSAR has tremendous potential. It is a sensitive indicator of change. It can be used to track very subtle differences in restoration progress. We can use it to look at risks associated with peat failures, etc. And we can also use it for quantifying carbon emissions from the land. And I think with that, I will stop there. So thank you very much for listening.
Hi, good afternoon. Hopefully you can hear me. Right, we're going to go into questions, and hopefully everybody else is up on the screen. That's it. Excellent. So lovely to be here. Okay, we'll go straight into the questions. So the first one, even though it later said it was answered, but I was still going to answer it. So can this be used in any way to measure peat depth by proxy or direct ground truthing imagery with field measurements? So I think that was to Paul and Becky originally, but I think it would probably still be relevant to the others as well. So if anybody wants to come in and answer that as well, how does their system relate to peat depth? And later on, there's a particular question on the InSAR work that David just presented as well on that peat depth.
Well, I think you originally, I'm not sure if the question was aimed at myself and Becky originally or not, but our focus has been using optical satellite data in conjunction with optical aerial data to identify the extent of bare peat. You wouldn't be able to use any of that approach to identify peat depth. The only option I know that comes anywhere close to that is the radiometric data that was explained in the following presentation. So that would be the way to go about it in a remote sensing sense.
With respect to the InSAR, there is some indication, we haven't followed this through yet, that the response of deep peat during the 2018 drought was quite distinct. You got particularly severe subsidence over deep peat, and that would relate to the landscape hydrology. And this was something we were supposed to be testing this year in the field, but COVID rather got in the way, so that remains to be tested. But under normal circumstances, the signal wouldn't be used for peat depth, but the drought response appeared to indicate it could be.
Thank you very much. That's great. So yeah, so you're going to look into that in more detail, which would really help and fill in those gaps. So questions for Naomi. Is the radiometric data available nationally? So you obviously looked at Dartmoor. How much does it cost? And this would be a massive step forward in our understanding of peat depth if available.
Okay, so it's available patchy. Big chunk of Northern Ireland has it, and because it's associated with looking for mineral wealth, areas of the country with mineral wealth, it tends to be, and we're just lucky in the southwest that we've got both. I have no idea how much it costs. because it was part of a NERC project that was done anyway, and we were just lucky enough to lie in an area where it happened. But it is a fairly standard geophysical airborne survey technique, and the equipment is available in the UK. So I don't know what doors we have to knock on to get it done, but it's not a crazy unusual technique. I don't know if that answers the question. So yeah, if you have a look on the TELUS website, they've got patches for other areas of the country, and if you're lucky, you will have it. And if you're not, then you have to pull some strings, maybe.
Okay, excellent. Thank you very much. Is there any assessment of the amount of ground truthing required to guide how many projects people to involve? So I'll put that out to everybody. So, you know, obviously ground truthing, important part to link to the information we're getting from, but how much is the right amount? Or I should think everybody's going to say more the better, but is there a ideal amount? Shall we start to the rapid satellite monitoring group, because we haven't heard from them yet? Is that a good place to start? Because
yeah, Jenny, do you want to come in here?
If I can find my unmute button. So yes, I guess the more the better is the short response. When we've been doing work before, looking at trying to assign peak condition to Sentinel-2 level tiles, so 100 kilometres squares, 300 to 400 data points really across whatever condition you're trying to assign, condition sets you're trying to assign. And it's also useful to be able to have an independent data set to be able to validate your model against. Otherwise, potentially you can end up showing your model predicts what you told it to predict really quite accurately, but it doesn't necessarily tell you how it predicts where you haven't got data.
thanks a lot. Paul and Becky, then, same question to you.
Well, yes, I would agree with what your summary, Ian. Yes, it's always the more the better. We don't have anything specifically from the study that was presented to assess that particular question, but I think the important thing that we need to be starting to think about is about how we collect this data and what we're wanting to use it for. And so, you know, it's interesting that the CEH presentation was talking about protocols designed specifically to get data rapidly collected that is suitable for using with the analysis of the Earth observation data. And that is exactly the sort of thing we need to be doing. We have potential under various national schemes that get volunteer surveyors out into the countryside collecting data on species presence and so on. You know, if there are simple protocols that can be sensibly designed, and we could start to utilize that sort of resource, then I think we could start to boost the amount of data that we get. But obviously, the more technical the data you need, if you need permanent water table monitoring stations and things like that, that becomes more difficult. But you know, if there are simple protocols that we can demonstrate that work well with the Earth observation analyses, then we need to think about how we can get those out and into the countryside and the data being collected. So a bit not a direct answer to the question, a slight tangent. Sorry about that, Ian.
Yeah, just a bit further to that as well. Yeah, I definitely second that. Actually having proper targeted validation data for the outputs that we're producing is yeah, something that particularly for our study we found was key, and you need something appropriate to compare against.
Thank you. Did anybody else want to come in on that? Or?
Yeah, I'd just like to add, it's not just about the number, it's also about making sure that all the different categories that you're trying to represent are sufficiently represented, because we have some habitat classes across Dartmoor that are quite small in their geographical extent, but they're quite important. So trying to get enough representative samples from these small areas has been quite difficult. It's quite a challenge, whereas the much more extensive acid grasslands, we've got loads of those. So it's that side of things as well, not just number, but actually what you're capturing.
So that if you go for a lot more classes, it becomes a lot harder to get good data to train your satellite models off, really. Well,
it can be a balance, because if you get more classes, you can catch the subtlety between them. You know, if you lump things in too much, they can be hard to differentiate if you've got a lot of within class variability. But yeah, you need to make sure that once you've dropped things down into their little groups, that they're represented enough to actually train whatever you're using to identify stuff.
Okay, that's very useful. Thank you. Right, I was going to go to the next question. So we talked about peat depth a bit, but we've got a question here about could we identify water table depth using remote sensing? And I guess in InSAR, David does that more than the other methodologies, but if we come to you first, and then
not particularly well. To get significant penetration of the radar into the peat, you would require water moisture contents less than 10%. We monitored the moisture through the 2018 drought over the far north of Scotland. It was really dry up there, and at no point in the very near surface did it significantly drop below 30%. So the penetration into what you think of as the ground, you know, what your foot would be on, is really quite negligible. So I suspect it's going to be relatively limited in its application for that, but there are others who are working on that. So University of Stirling are doing some work on that, and who knows, maybe you could pull out enough sensitivity to do it. But the InSAR per se is not profoundly affected by water depth, and there's little evidence to support that.
If I could just add to that, I have seen one paper published that was a study in Eastern Europe, and I can't remember exactly where, that was trying to relate InSAR data to water table depth, but it's only one study, and I haven't heard anything about a follow-up. So I would trust David's knowledge on that far more.
Where the InSAR will indicate water depth, it does it indirectly, is that the deeper the water, the less the elastic response will be to a change in the water level. So the reason you get that ground motion is because of the elastic response of the peat surface to a change in the water level. The water table is very deep, then you simply lack that elastic response because it's in degraded peat. If the water table is very shallow, you get this very large dynamic motion, high amplitude motion of the peat surface. And that is indirectly indicative of water table depth through the mechanical behaviour.
Did the others on Dartmoor or in Wales look at that, or think their methodologies can show that at all?
The only thing we've done looking at water tables in any way using the remote sensing data, as far as I'm aware, is a few years ago we used thermal broadband imaging to look at near surface wetness, and that was only one discrete data set, so it's not been part of what we've been trying to deliver in the southwest so far.
So in Wales, again, we've not been trying to directly measure water table, so you can infer it from what vegetation data, peat condition you're picking up. So you pick up the vegetation associated with drier peat areas rather than wetter ones, but we've not been able to pick up anything directly on water table.
So yeah, particularly looking at sphagnum and things like that, that you'll get more in the wetter areas, presumably. Okay, excellent. So somebody asked here again, I think this is about InSAR, could we develop an early warning system similar to earthquakes across peatlands worldwide? So that's a question for David, I think.
I reckon you could. I don't think it's quite the same as earthquakes. Earthquakes are highly unpredictable. I'm a geologist in background, so I know a fair bit about earthquakes. I think the process to peat failure is probably much more systematic. I think it's to do with a build-up of peat mass, subtle and prolonged changes in hydrology, accumulation of mass of water in the system, and probably gradual weakening due to high amplitude oscillations. This is speculative still, so that needs to be tested, but I imagine that InSAR would be potentially quite indicative of areas that were prone to failure through these very high amplitude oscillations of the surface, which is caused by effectively excess water pressure. So I imagine you could. I think there's a lot more work to demonstrate that, and what we hope to do is test this out over the UK and Ireland, compare predictions to observations and see whether it makes sense. Suggesting so far as it probably will, but we need to test it, and that's probably about a year away from getting a good test of that.
Okay, thank you. I'm going to ask, so the Welsh rapid satellite monitoring, so probably to Jenny, I guess, originally. So are the resources you mentioned available on the CEH website, was the question. So how much of this is available and accessible?
Do you want me to come in here, Jenny?
Yeah.
Okay. So UKCEH have been working with the Welsh Peatlands SMS project to develop these protocols. So the rapid assessment we've been using out and about and tweaking it here and there. So that will be, I think, available after this, but also we're going to be presenting that in the exhibition hall. And then we've also done a more detailed method, which then builds on that sort of bolt-on methods. We might have a discussion about that in the research session later on as well. I'm not sure. And we've also got a protocol on the QField app, which is what we've been using, although there are others available through ArcGIS and others. So that's where they'll be during this conference. I'm not sure if they'll be on the CEH website. Maybe Annette, you can come in on that. But we want to be widely available for everyone across Wales and even outside of Wales as well.
Yeah, CEH will be publishing them very soon. It's just gone through our kind of internal project team, and as Rachel said, as we've been using it, tweaking it a little bit, but that's all done now really. So we'll be publishing them through CEH.
Excellent, thank you very much. Right, I'm going to go on to the next question then. Does the resolution of satellite data cause smoothing, which would lead to underestimation of eroding peatlands at landscape scale? We compared high resolution UAV with 5-meter DSM, and highly eroded areas look flat at the 5-meter scale. Would anyone like to have a go at answering that?
I can come in there if so. I mean, our study wasn't looking at the topography of the surface. It was looking specifically for how much of the area is unvegetated, which is a signal we can pick up from the optical data. I'm sure you would get a smoothing effect just because of the lower resolution. I think that would be inevitable. But that sort of effect was part of the reason why we were so interested in looking into this modelling method, whereby the models are generating an assessment of the quantity within each pixel that was unvegetated. So you're getting a percentage per pixel, and as Becky said in the presentation, this came from some original research that was done by CEH and James Hutton for the DEFRA Earth Observation Centre of Excellence, and we've just worked that up to to test it further. So that is an approach to try and reduce that level of smoothing, but it's not looking at the topographic nature and the shape of the surface. So it's not directly relevant to the question, I don't think.
I'm going to just add to that. I think that you obviously get smoothing using data of different fixed resolutions or process resolutions, but it's also worth bearing in mind that the way those data are derived incorporate quite specific differences in how a surface might be understood or modelled. So if you're using structure from motion derived UAV models, they're going to have a lot of fine resolution or fine scale data, but they'll actually have a whole additional set of uncertainties which are very different to something like LiDAR or SAR derived DMs or DSMs. So it's not just the resolution, it's about how the remote sensing technique interacts with the surface it's measuring, really.
Okay, excellent, thank you. I think we'll just squeeze one more question in before we finish then. So this is to David again. How much does the InSAR based condition classification need to be calibrated to an area? Could it be easily translated to, e.g., the Pennine blanket bog? So can you take it from one area and
absolutely
put it in a different area? And I guess that's at this large scale. But
across Scotland, for lowland raised bogs, blanket bogs, it appears to show very similar characteristic behaviours across all of those. The application of it, I imagine, to the Pennines would be straightforward. I would have no concern there. I think I'd have more concern moving into fens. We haven't really looked at fens, so I think there's an awful lot more water management goes on in fens, a lot more agriculture going on. So I think that's an area where I'd be very cautious at present. But we've applied it to a lot of different areas, and the same principles seem to apply. It's the response to changes in water storage that causes the surface motion, and if the peat properties are different and the way it responds to water storage is therefore different, then you should see similar patterns of behaviour and be able to assess the condition in a similar way.
Thank you very much. I'm going to close the session there, but I'd just like to thank all our speakers and the wonderful presentations we had, and everybody that's inputted into those projects. They are really amazing how much we're moving forward in this field at the moment. Thank you very much.